So if we look at a titration curve, an O2 titration curve of hemoglobin, what we see is what's shown here in the black dots in the figure here on the right. And no matter what we do, if we use the hyperbolic binding function that we learned for myoglobin, we cannot fit this. If we set P50 to 4 torr, what we see is we bind really well in the saturation point, but we completely miss this curvature in the sigmoidal region of hemoglobin. If we go lower, if we go to a lower affinity, such as a P50 of 400 torr, what we do is we fit really well at low oxygen concentrations, but again, we don't fit the rest of the curve very well. We have what's called systematic deviation. And then even if we do the trick that I taught you for this curve where we go at theta equals 0.5 and then project down to the x-axis, we would get a P50 of 26 torr. If we use this equation, again, the hyperbolic ligand binding equation shown here in the figure, and plugged in 26 torr, we would go through the middle of this curve, but you see that it doesn't fit very well either at low oxygen or at high oxygen. What that suggests is that our model is incorrect, our mathematical model is incorrect. And our mathematical model in this case is based on a reaction where the protein binds to ligand to form PL. Now that's only one ligand. Now remember that hemoglobin is a tetramer. So in principle, you can think you think of the tetramer as the protein. So that is P in this case. And there are 4 heme sites because this is a tetramer. So if you instead think of this as being able to bind several ligands simultaneously, then what happens is that you write an equation where P plus NL, where N is the number of binding sites, in this case the number of O2 binding sites, and the maximum number we can have is 4. And that is in equilibrium to form a protein that is bound to N number of binding sites. So again, in this case, the maximum number would be 4 for hemoglobin. If we use that and create a mathematical model instead, we get a different equation. And so this is what, I won't derive this, and you won't be expected to know how to derive this, but what we show here is that in this case, instead of the simple hyperbolic equation that we showed before, what we get is theta equals ligand to the nth power. Again, n is the number of binding sites, but it doesn't necessarily mean, n will not necessarily tell you how many binding sites there are. I'll tell you in a second what we actually use that number for, but all you need to know is that n should be greater than 1 for greater than or less than 1 if there is what's called cooperativity. On the bottom is L to the nth power plus KD, and KD has a similar meaning to what it meant before for the myoglobin binding curve. We can rearrange this using mathematical functions to this equation. So if we rearrange this using logarithms, what we get is the log of theta over 1 minus theta equals n times the log of the ligand minus the log of KD. In our case, just to clarify, remember what we're using in place of ligand is the partial pressure of the oxygen, and KD we're replacing with P50. So our equation in this case is log of theta minus 1 over 1 minus theta equals n times the log of PO2 minus the log of P50. Okay? And so the form of this equation, in either this form, is called the Hill equation. And we can use this to fit sigmoidal O2 binding plots, such as that observed for hemoglobin. Now, what this actually means, what this is actually telling us, is if we can fit this binding curve to a Hill equation, what that is indicative of is a phenomenon called cooperativity. And we'll get to what the structural basis of cooperativity is, but essentially what it means is that the binding of a ligand to one of the binding sites on the protein. So again, in the tetramer of hemoglobin, if O2 is bound to one of the hemes, then what that means is that in cooperativity, that this binding influences the binding affinities of the other heme sites within hemoglobin. And so by fitting this equation and transforming the data, what we get is a plot that looks like this on the right-hand side. We're at low O2 concentration and high O2 concentration. We have very similar slopes. The slope changes at an intermediate oxygen concentration, and if we fit a line to that, what we can get is a slope that tells us what n is equal to. For a Hill plot, if n is equal to 1, there is no cooperativity. If n is greater than 1, then what we have is called positive cooperativity. And if n is less than 1, then we have what's called negative cooperativity. And we'll define those in the next few slides.